a live stream question and answer session about astronomy. And as Professor Impey likes to say, we'll answer all of your questions from comets to cosmology. I'm sorry I stole your line, but it's a great one. So I will let you welcome everybody and we'll get started right away with questions.
Okay, yes, another live session for the online classes or anyone who happens in on these sessions. I'm happy to answer questions on any topic. So we can go ahead right now.
All right, the first question is from Irene Kitzman, who is on with us live. What is the underlying theoretical or physical basis underlying the finding that gravitational waves move at the speed of light? These waves have nothing at all in common with electromagnetic waves, so it seems kind of confusing.
Right. Hey, Irene. So it's a good question. Gravitational waves, the theory of them emerged from general relativity. Einstein did some of that work, but actually other researchers in the 20s and 30s developed the formalism for gravitational waves. So basically, it comes straight out of general relativity, straight out of the idea that mass and energy warp space and time, that any impulse coming from gravity will travel at the speed of light. So it drops out of the theory, basically, which means it's a prediction of general relativity, but it is one that hasn't been directly confirmed. It's only been indirectly confirmed. And in the sense of being indirectly confirmed, it's the fact that we know the sources of a set of the gravity wave detections we've had so far. There have been over 20 now. And from all sorts of distances ranging up to 10 billion light years, but mostly a few billion light years away. So we can see what the target is. We know the distance of the target and the time ago that the target is being seen. And when we have an optical identification of the target or even the target galaxy within which the merging black holes exist, then we sort of have a corroboration of how old that information is when it reached the telescope. That's not the same as an actual measurement of the transit time and speed in transit of a space-time perturbation, but it's as close as we can do right now.
And then can you talk a little bit about what the implications, the astrophysical implications are, given that gravitational waves do travel at the speed of light?
Well, the astrophysical implications are just as they are for optical and electromagnetic wave astronomy, that, looking out in space is looking back in time. So a telescope, even a telescope like LIGO, is a time machine, allowing us to look back in the history of the universe. Now, the extreme version of that for gravitational waves will come because there are predictions that the Big Bang itself could generate stochastic or certain power spectrum gravitational wave signatures that are characteristic perhaps of inflation. And so there are theories that make predictions about that. And that gravitational wave background, because it's not a single event like a pulse that you get from merging black holes, it's more a continuous signal. That is a characteristic that people hope to look for in the next generation of gravitational wave detectors. So that will be an extreme version of this idea that we're looking out in space and back in time, because there's a chance that we may actually be able to diagnose physics at the inflationary epoch in the first tiny fraction of a second after the Big Bang by the detection of gravity waves from the Big Bang with a terrestrial-based gravity wave telescope.
The next question is from David Learning, who's on with us live. What exactly is broken symmetry and how does it apply to astronomy?
A broken symmetry is an idea in physics which holds that generally at the highest energies attainable, there's a unity in physics. For example, the four forces of nature are presumed to have been unified into a superforce at some incredible temperature and some incredible early epoch in the universe. And then after that, as the temperature falls, then different forces of nature freeze out, in a sense, freeze out because the temperature is going down, and they have quite particular characteristics. So symmetry is sort of implying that everything's the same or everything looks the same. When the symmetry is broken, we have quite distinct properties of a force of nature or of a subatomic particle and so on. So that's the idea of broken symmetry. And there are other examples of this in physics, but that's the astrophysical version.
Excellent, thank you. Our Jacent, who's on with us live, asks, can you explain black hole evaporation, Hawking radiation, and how this differs from what quasars emit?
Sure. I mean, we've had a number of questions about Hawking radiation and black hole evaporation, but I can summarize. Um, and particularly the difference between what's seen going on in quasars. The emission that's seen in quasars is high energy electromagnetic radiation produced in the vicinity of a black hole. So although the black hole that powers quasars are very massive, they're inferred to be hundreds of millions or billions of solar masses, and the black holes themselves are dark, they're in the middle of galaxies with a lot of material. And so that material swirls into an accretion disk, is heated up. That heated disk can collimate material along the poles of the spin axis of the black hole and accelerate particles at close to the speed of light. So you have the ironic situation that a black hole, a dark object, is generating an intense radiation environment, and that's what we see as a quasar. Now, the Hawking radiation from a black hole is something totally different. That's an intrinsic property of the black hole itself, inferred or imputed by Hawking's ideas in the 1970s. And it has not yet been detected. So Hawking radiation, especially compared to the kind of radiation from an accretion disk around a black hole, which is really intense, is incredibly subtle. The Hawking temperature of black holes is a tiny fraction of a degree Kelvin. And so the radiation would come out at extremely long radio wavelengths. And it's an undetectably weak and long wavelength radiation. So the real problem is we don't have a physical way of detecting Hawking radiation, which would amount to proof that black holes have a temperature and also proof indirectly that they do evaporate.
Excellent. The next question is from Wendy Traver, who sent an email. Professor Sean Carroll wrote in an article that space is made of fields and particles should be thought of as excitations of those fields. So the Higgs boson is an excitation of the Higgs field, but then can mass be thought of as analogous to a proton, electron, or is it special in some way?
Well, in the notion of the Higgs field or the Higgs particle, that's right. The Higgs field is what is really fundamental in the concept, and the field is presumed to permeate space. And then it's the interactions with this field of something that we will call a particle that give the particle its properties. So if we imagine certain types of particles have a high viscosity with respect to this field, then they will have a lot of inertia, and we'll see them as massive particles. Particles that interact weakly with the Higgs field or have a low viscosity, say, will have a low mass and maybe move closer to the speed of light. So we impute the properties of particles, what we call subatomic particles, by the way they interact, and in a sense by the way their properties are generated by the Higgs field itself. So it's the Higgs field that's fundamental in this and not the particles themselves. They're sort of secondary manifestations of the Higgs field.
Along the lines of particle physics, we'll take a question from Jan Campos, who asks, if fusion holds a main sequence star in hydrostatic equilibrium and degeneracy pressure maintains a white dwarf and neutron degeneracy pressure supports a neutron star, is there anything supporting a black hole?
No, it's a good question. Right, these other objects are late stages of stellar evolution, the white dwarf and the neutron star state in particularly, which the only thing that stops the star collapsing further is a force of nature that we understand as this degeneracy pressure, which is basically the inability in quantum physics for two particles, either electrons in the case of a white dwarf, or neutrons in the case of a neutron star, to have exactly the same quantum properties. This manifests as a pressure, which keeps the star at a finite size. Black holes have no such force, and essentially a black hole is an object where the mass is sufficient to overcome even the neutron degeneracy pressure. The implication of this, in fact, is that the center of the star collapses to nothing, and that's the origin of the idea of a singularity, which is an unphysical concept. So black holes contain a bit of a problem because compared to these other end states of stars, we don't really physically understand the center of a black hole, since the theory predicts collapse to a point, which is an infinite mass density. And then our view of that infinite mass density, or that cusp or singularity, is obscured by the event horizon.
And then kind of a follow-up question, is degeneracy pressure a much more powerful force than fusion? Does it create more light and heat?
It's not an energy generating mechanism. It's essentially a pressure. So it functions as a pressure, but it functions as a pressure without the release of energy or radiation. So like I said, degeneracy pressure, regardless of its cause, is associated with the quantum properties of fundamental particles. And essentially, the Fermi exclusion principle, which says essentially, especially that two electrons or two subatomic particles can't have exactly the same quantum properties, all told, all the different quantum properties. That means that they are essentially can't be the same as each other. And so that amounts in physics terms, in subatomic physics terms, to a pressure. So it's not really analogous to fusion at all. So fusion is a nuclear reaction, a reaction between particles that leads to the emission of energy and radiation. And it's that radiation and that pressure associated with that radiation that keeps the star puffed up like the sun. And it's really quite different from degeneracy pressure, which is a purely quantum property of matter and is not associated with the release of radiation.
The next question is from Tianis Kuto, who's on with us live. Alien life has to be more different from us than we Earthlings are from each other. And but even terrestrial beings have different senses based on the environments we live in. Is it possible that we could imagine what the possible senses different alien life might have or use, and use that as a method to find that life in space, sort of like using sound to see in a dark room?
Right. So there's a whole history and sort of tradition of speculating about the nature of alien intelligence, and there's another tradition about speculating about the nature of alien physiology, and in particular their sensory apparatus. Arguments have been made that since stars are fundamental in the universe and they are the primary energy source, we think, of many life forms, not life forms that live underground, but those that live on the surface of a terrestrial planet, that other life forms elsewhere in the universe will evolve to sense that radiation, since it's fundamental to their existence. And so something like an optical sensor, maybe not exactly looking like an eye, but maybe because an eye focuses radiation quite efficiently, could be a more universal feature of biology than we might imagine. Similarly, if life exists on a planet with an atmosphere, which it will have to do as a shielding blanket around the planet, and as a medium, you can't have a planet with a vacuum that could support life. The radiation would be too intense and the pressure would be too low. So the life forms containers essentially would explode. So therefore, if atmospheres are a fundamental feature, then sound will have properties traveling through atmospheres as pressure waves. And so maybe alien creatures also have something analogous to an ear to sense those oscillations, those vibrations of the atmosphere they live in. So these are examples where the properties that lead to life in other situations, the physics of that environment could lead to very similar sort of sensory apparatus that we have. Now, this could look totally different. The architecture of the sensory apparatus might be way different in the physiology and the size and in the efficiency of how it works and the wavelength range and frequency range that it works and so on. But there's some possibility that there are equivalents elsewhere in space.
The next question is from Dan Mull 321. In one of the previous sessions, you mentioned that after the Big Bang, the universe expanded faster than the speed of light. But how is that possible? I assume that is based on the size of the visible universe and the age of the universe. So how do we think it happened, and then how do we know that it might have happened this way?
Well, when we trace back the cosmic expansion, given our knowledge of the mass and energy density of the universe, we simply and easily infer in the Big Bang model that there was a period of time really amounting to the first 4 or 5 billion years after the Big Bang, so roughly the first third of the universe's age so far, where any 2 points in space-time were moving faster than light speed away from each other. So it's just a simple prediction of the Big Bang model working backwards, that the universal expansion has decelerated initially from its very rapid rate, faster than light, and then more recently has been accelerating due to dark energy. So how can that happen? How can that be? And it's very simple. It's because the speed of light as a limit in physics and carrying signals is a function of special relativity. But the expanding universe is governed by general relativity, which is a more overarching theory of gravity and nature that Einstein came up with. Just the words special and general essentially tell you the difference. And general relativity has no speed limit attached in it. The speed of light does not appear as a fundamental limit in general relativity anywhere. It does appear as the speed of propagation of a space-time perturbation or gravity wave, as mentioned before. But it doesn't appear as a speed limit on how fast space-time can expand. So it did, we think, expand faster than light speed for a good fraction of the age of the universe.
Charlie Hollis asks, Fermilab's Magus 100 detectors designed to try and detect dark matter. Do you think that this may be viable?
Yes, Fermilab and a number of labs, maybe a dozen around the world, mostly underground detectors, are using solid-state technology to try and detect dark matter. Essentially, they're looking for the very rare interactions of a dark matter particle, where it's hypothesized that that dark matter particle is a fairly massive particle that essentially has no interactions with radiation, so you can't detect it by the way it absorbs or scatters light. But it does have mass, and so it will interact with a solid-state substrate, a medium like pure silicon or even a gaseous medium, and it will impart energy to any particle that it hits in that detector or that medium. And so you're essentially looking for the collision energy of the dark matter particle. But even those interactions are extremely rare. So you need a very pure detector. You need an enormous number of atoms to possibly receive this interaction with the dark matter particle, since it's so rare. And you need very sensitive detectors to pluck out that signal, since it may be so rare and occurring in a large volume of a detector. So the Fermilab instrument works in this way, as do many of the others around the world.
A related question, the decay of the B meson particle might suggest a new model of physics is needed in light of recent research at CERN. Do you think that the standard model is wrong or just incomplete?
There's tantalizing evidence out of CERN in the last few months, and it involves the B meson. It involves a departure from the predictions of the so-called standard model of particle physics, where there should be sort of equal components of decay products in the different flavors of particles. So there are three families of particles, as we know. There are the electron, the muon, and the tau. Those are the fundamental particles, and there's also electron, muon, and tau neutrinos. And the standard model of particle physics predicts equal pathways in this B meson collision case for those pathways, those three types of particles, those three families. And that wasn't what it was observed. So this is a departure from standard physics, which is exciting because the standard model of particle physics is known to be incomplete, but CERN has had very limited success in finding new physics. Now, it's worth pointing out that I think the first detection that's been covered in the press is just over a 3 sigma detection, 3.1, I think, which means formally the odds of it being a chance event are about 99.5, 99.9%. And that sounds pretty good, like 1 in 1,000 chances of being wrong, but it's not good enough for particle physics. Particle physics essentially insists on a 5 sigma detection, which is like 1 in a million chance you got it wrong. So this is the kind of result that unfortunately occurs quite a lot in particle physics. It's tantalizing, but it's not at the gold-plated significance level that means it can be counted as a discovery and new physics.
The next question is from Egil Scala, who's on with us live. Some scientists think life might have started on the surface of Venus. At what point in the geologic history of Venus did the surface become uninhabitable for any form of life?
Venus has been uninhabitable actually for quite a long time, so possibly for 3 billion years. But if you go back 3 billion years, that's the last time at which it's possible that the latest time that Venus might have been temperate. And that's the time people speculate that Venus could have hosted life. So Venus is obviously a heavily volcanic planet. It's one of the most volcanic worlds in the solar system, and it's had enormous waves of volcanism. The most recent one, I think, was 700 million years ago, when a good fraction of the surface was coated with lava, fresh lava. And of course, that generates a lot of carbon dioxide. So the volcanism of Venus has, of course, contributed to carbon dioxide in its atmosphere. And at some point, it passed the tipping point where, as a fairly massive planet, a twin of the Earth, it could retain the carbon dioxide. And as more was produced by volcanism, you set up a runaway greenhouse effect. So we don't know exactly when that happened, but it probably happened a couple of billion years ago, and Venus has been uninhabitable since then. And so we see it now in a very bad state of greenhouse runaway, where the surface temperature is 700 degrees and lead would melt on the surface, and we don't imagine there could have been life there. But it's quite possible that Venus could have hosted life in its distant past.
The next question is from an email. Is it possible that an asteroid or comet impact with another planet in the solar system could reconfigure our solar system?
The idea of collisions rearranging planets in their orbits is a real idea in planetary science, but it almost always only applies in the very first stages of formation of a solar system, when objects are being built. So in the building phase of planets, there are a lot of collisions, because basically 1,000 or 10,000 planetesimals, that is, 1,000-kilometer sized chunks of rock, are combining to form the planets. And sometimes the planets get smashed by that process and collide into each other, and so on. And then the planetary system stabilizes after 50 or 60 million years. Thereafter, collisions are extremely rare. Now, subsequent to that, there can be rearrangements of the planets due to orbital instabilities and resonances, and we think that happened in our solar system. But planet rearrangement by collisions is extremely unlikely to happen after the formation phase. Also, asteroids and comets are really small. Comets, of course, are about 5 or 10 kilometers across. Asteroids, of course, can be much bigger, hundreds of kilometers. But even then, only the very biggest asteroid would be a planet-shattering event, and the odds of that happening in a mature solar system are very low.
The next question is from Christina Vislapu, who asks, could you explain the difference between plasma, like inside of stars, and the state of matter under super pressure, like the gas giants?
Right. So plasma is just a general term in physics for any gas that's hot enough that the electrons have been stripped from the nuclei. And so it's a general term, and the sun is a plasma, and the centers of giant stars and massive stars of any kind is a plasma. So essentially all of the stellar interiors of any kind of star, it fits the definition of a plasma. It's a general term in physics.
Sorry about that. The next question is from one of our live participants, who is Tingerman Alf. And what is outside the universe, since the universe has boundaries?
Well, the universe doesn't have physical boundaries that we know of. We've not found a physical boundary, and there's no reason to hypothesize one. All the universe really has is a boundary of visibility. That is, it has a horizon. And in cosmological terms, a horizon is the limit we can see based on the time available for light to travel to us. So the universe has a finite age, 13.8 billion years. And so light can only have traveled a certain distance in that time. And that distance in any direction represents the horizon of the universe. So that's the only real boundary we can speak of in the universe. It's a visibility boundary. It doesn't mean it's a physical edge or the end of space-time at all.
The next question is from one of our live participants. When you graduate with a degree in astronomy, I'm not sure if they mean undergraduate or graduate, but they would like to know, what are the possibilities of work in the field? What kind of work do you do being an astronomer?
Right. So the basis of an astronomer is a degree, an undergraduate degree, and then to do research, a graduate degree, because it's only really, many undergraduates get a research experience, but it's only as a graduate student that you really learn how to do independent research. So if the goal is to do research in astronomy, then you need a graduate degree. Students who have an astronomy degree at the undergraduate level, however, can still work in astronomy in different ways. Definitely you can work in an observatory. Telescope operators and engineers and technicians at major observatories don't need an advanced degree in astronomy. Sometimes they don't even need an undergraduate degree, but it helps. So there are certain jobs, maybe more limited jobs as an undergraduate to work in astronomy, especially at an observatory. With a graduate degree, of course, you're in a different realm because now you're showing that you're able to do independent research. And at that point, you have the ability to be a researcher in a major institute, a NASA institute or a national lab, or to work in a university on an academic track, maybe first as a postdoc and then as a faculty member or instructor. And that's what you can do with a PhD or a master's in astronomy. So the graduate degree is what is required to be able to do research in any employment setting in astronomy.
The next question is from Single Coded. There was a project, I think the name was HAVOC, High Altitude Venus Operational Concept, to send human or robotic operated Zeppelins to hover in the atmosphere of Venus where the temperature is moderate. Are you familiar with that? Is that mission still active? Is it something that's still being worked on?
Yes, I think that's still an active concept. NASA, is belatedly getting interested in Venus again. Some planetary scientists are slightly annoyed at the obsessive level of interest in Mars. Nothing wrong with Mars, exciting place to go, but they think it's just had over much attention over the last decade or more. And so Venus missions have languished, and the one in the question is just one of them. There's a mission that was a lander, a Venus lander. We remember we hadn't landed on Venus till the Russians did it a few times in the 60s. So there are several mission concepts, orbiters, the sort of quasi-drone idea, a lander, and they all are in various stages of development and funding. And I don't think any has been approved at this point with a real launch date. But the interest in Venus is growing because it is the twin of the Earth. And there's a lot to learn by analogy, an example about the history of the Earth by studying Venus. And we've essentially sort of given up on Venus since the Magellan radar experiments in the 1970s mapped the surface. There's been very little space science approaches to Venus, and so it is overdue.
The next question is, it's several parts, so we'll start with one. It's from an email from Ravi. We've learned that the size and temperature of a body affects its atmosphere. However, I'm unable to reconcile the fact that Venus and Earth are similar in size. Venus is much closer to the sun and hotter, yet its atmosphere is much more dense than Earth. So how does that work? I mean, I guess, why hasn't it blown the atmosphere away? Or, what is it that causes, this atmospheric condition?
Right. So there's several things going on in Venus that differentiate it from the Earth. And we start with the fact that they're very similar massed planets within 10% of each other of size and mass. So they are pretty close to twins. Venus being 30% closer to the sun means that it receives almost twice as much radiation as the Earth. And so that means the surface temperature, just the natural surface temperature, regardless of atmosphere, will be somewhat higher. Then you add the second factor, which is that just for geological reasons, nothing particular or extreme, just Venus is more geologically active than the Earth by some degree. And that geological activity generates more carbon dioxide. So you have a much easier path to generating a thick atmosphere, for that atmosphere to be being hotter. And that heat again generates more carbon dioxide because carbon dioxide can disconnect from the rocks when there's sufficiently high temperature. And so you have a sort of positive cycle and a feedback loop. And that, of course, is the greenhouse effect that heats up the atmosphere even more because the radiation is trapped. So basically, while they were roughly similar planets, perhaps 3 or 3.5 billion years ago, they diverged quite rapidly because of these differences, so that now they are extremely different in their surface properties.
So then the next question is, with that being said, Titan, the moon, is tiny, cold, and far away, but has a more dense atmosphere than Earth. So how does that sort of relate to what you were talking about with Venus?
Right. So what is the relationship between the Earth and Titan, and why does Titan seem to have quite unusual properties? Titan is a large moon in the solar system, one of the handful of largest, but of course it's not nearly the size of the Earth. So it doesn't have the same surface gravity as the Earth, which makes it a little surprising that it can hold a thick atmosphere. Its thick atmosphere, which I don't think is twice as thick as the Earth, but it's significantly thicker and made of nitrogen as well, like the Earth's is, with none of the oxygen that we have. The fact that Titan can retain an atmosphere because it does have significant mass, because it's a lot colder out there, and the temperature of an atmosphere affects the rate at which gases escape into space. So basically, the higher the atmospheric temperature, the faster the molecules move, and the more likely they will just evaporate off into space over time. So Titan is at a cold temperature where it's not lost none of its atmosphere over cosmic time. And so that nitrogen, whatever nitrogen was released by cryovolcanism or geological activity, and Titan has geological activity this far from the sun, partly because of tidal heating, in fact, and because it has significant mass, so there's radioactive decay in the rock. So that heating, it generates more nitrogen, so thickens up the atmosphere, and so you can end up with a moon, not a full-fledged planet, that has a substantially thick nitrogen atmosphere, but also with none of the oxygen that the Earth has, and trace amounts of ethane, methane, carbon dioxide, acetylene, ammonia, and some other toxic gases.
And then finally, how does that relate to Mars's atmosphere? So again, Mars is kind of in the middle of the two of those, and yet it has almost no atmosphere and a small size. So
right. So Mars is half, it's a quarter of the mass of the Earth, and so the surface gravity is about 70%. And Mars is less able to retain an atmosphere. Carbon dioxide is the most natural atmosphere for any planet to have. Venus is mostly carbon dioxide. Mars has almost all carbon dioxide, and except for the nitrogen and oxygen, carbon dioxide is the third most abundant molecule in the Earth's atmosphere too. So you've got a natural atmosphere of Mars, and you have an atmosphere that's just leaked off into space over time, because the low gravity is insufficient to retain that molecule, given the average speed of the molecules and given the sun's radiation. So Mars is just at low enough mass that its ability to hang on to a thick atmosphere is compromised. Remember that Mars has also had geological activity, which in principle generates more carbon dioxide, but not recently. It's geologically very inactive and has been for hundreds of millions of years.
And the next question is, can you talk about the 3K echo of the universe? Does that indicate like a bubble, that it's, and there are more than one universe and many bubbles?
So the 3K, 3 degree Kelvin microwave background radiation is a relic radiation of the Big Bang. It's not really a bubble necessarily, because we see this radiation in every direction we look. So it essentially permeates space, and we measure it with essentially the same intensity and with essentially the same temperature in any direction we look. So it is essentially the ambient radiation of the Big Bang that's diluted, cooled, and stretched in wavelength since the Big Bang. There's no implication of places beyond that don't have this radiation, because the universe we see is the only one we know of. And so it's not like it's a bubble or a region of the universe that has this radiation. It essentially permeates space-time everywhere we can look.
The next question is from one of our live participants. How can you talk a little bit about how other people in other professions can get into astronomy after their graduation? This person asks specifically about electrical engineers, but can you just talk about some different kinds of careers in or related to astronomy, for people from a variety of backgrounds?
Right. The main pathways into astronomy through undergraduate and graduate degrees are physics and astronomy. Physics applied to the universe is astrophysics, and that's what astronomers do. So astrophysics and physics are very closely related. So apart from those two traditional pathways, the next most common pathways are actually sometimes through engineering. So electrical engineering is a possible pathway because you will have some base of mathematics and some physics probably. And you do need the math and the physics to be doing astronomy. Now, the training in engineering, of course, makes you potentially useful in an astronomical setting to work on instrumentation, to work on spacecraft, to work on telescopes, to work on satellites, and so on. So electrical engineering is kind of a useful degree, not so much for doing astronomy research, but being associated with astronomy projects, major missions and projects and telescopes. Other forms of engineering are not quite as directly applicable. Computer science, of course, is another indirect pathway into astronomy because astronomers use programming and computer science methods very frequently. They work with large computers. They have to run simulations, not just of the universe or pieces of astrophysics, but of instruments, of observations they make, and so on. So computational techniques are very important in astronomy at the research level. So computer science is an interesting way into astronomy, but again, to work as a functioning astronomer, you need the physics and the math as well to be able to get there. Pure math is another way in, less common. I don't know very many people who came into astronomy straight out of pure math. Obviously, at this point, you're aiming towards being a theorist, but then you would need quite a lot of physics too, because the theory of astronomy is really, again, physics theory applied to the universe. So these are the main pathways that I'm aware of. They all do amount to a small fraction of the people who go in through the traditional routes of physics and astronomy, either together or separately.
The next question is from Osmanulu, who's on with us live. Earth is thriving with life now, with an abundance of organisms everywhere. Does this suggest that another world we may find should also be thriving with life? And if so, are we prepared for it?
I mean, it's a great question that we really want to know the answer to now, having found thousands of exoplanets, including hundreds that are Earth-like planets. So the question really amounts to, if you had an Earth clone or a set of Earth clones, just completely Earth-like planets, as they formed in every aspect except biology, lit by a sun-like star with the same radiation as the sun, and you just watch them evolve, what would happen? Would you end up with biology on any of them? And we simply don't know the answer to that question. It's a really important question. Some people say, without evidence, but their hunch is that, yes, we'd find life or biology on all of them eventually if we waited long enough. And other people say the process by which life started involves some unlikely steps, or molecules going quite a long way down the road from simple to complex, and the formation of the first cell and the energy and information storage mechanisms of biology are very specific, and they seem unlikely to form naturally, although they can over time. And so they will argue that these Earth clones that we hypothesize might not have life. Maybe none of them would, except the Earth. So we're in a very high degree of uncertainty about this. But yes, it does seem plausible that if you were given identical planet to the Earth and all the conditions that life on Earth started with, that the same thing would happen there too.
The next question is from Sutanuka. Since the second image of the black hole is now being captured with its magnetic field lines perfectly captured, how soon are there any chances that we might be able to see what's inside of a black hole, which is certainly not black?
Right. So this is an exciting image that was published recently from the Event Horizon Telescope group. It's the M87 black hole, the massive black hole that the spectacular image was first released of about a year ago. The new ingredient here is they measured the polarization of the radiation. And the polarization of radiation in an environment near a black hole reflects the presence of magnetic fields. So we think the black hole itself, as a collapsed quasi-stellar object, and the accretion disk around it is threaded with magnetic field. And so the radiation that is emitted in a magnetic field is typically synchrotron radiation, and that's polarized. So that's what the polarization is doing. It's tracing magnetic field. It doesn't get us any closer to seeing into the event horizon, however. This new image is just adding an extra layer of detail on this radiation by imputing the magnetic field. It's still magnetic field outside the black hole. It's radiating the accretion disk, and it doesn't tell us anything more about inside the accretion, inside the event horizon.
The next question is from Tana, who would like to know about space tourism. There's a project named Space Adventures, and there are undoubtedly other space tourism companies out there. Can you talk about how these might work in the future and what you think the future of space tourism might be?
Yeah, space tourism is something that we think is going to happen. The leading companies, of course, are SpaceX and Virgin Galactic. Now, SpaceX we've heard a lot from because they've been very successful in launching astronauts for the first time to the space station. And so they're making their money by working with NASA on delivering initially supplies and then astronauts into Earth orbit. But their long-term goal involves tourism, so they want to eventually open up what they're doing with rockets and NASA astronauts to civilians who are paying money for it. Virgin Galactic is doing suborbital flight, so it's quite different. They're not going for Earth orbit, what Elon Musk is. They're literally straight going for the tourism angle of a sort of 15-minute zero-gravity joyride in what amounts to low Earth orbit, 100 kilometers up past the Kármán line, which is the formal edge of space. And they've requalified their craft, which had a fatal accident a few years ago, and so they're back on track for commercial launches probably in 2 years. Space Adventures, other company mentioned, they have ambitious plans. They were involved in some of the space tourists, the first dozen space tourists who went on the Soyuz to the space station. And as a company, they're planning very ambitious, not just Earth orbit, but actually visits to the moon, and they've started advanced planning for that. And if you put it all together, there's about 24 private space companies, about half of which are actively pursuing space tourism of some kind involving paying members of the public, paying quite heavily, of course, initially, millions of dollars, and then hopefully eventually the cost comes down. So it's a vibrant sector of the space economy that's just at its very beginning stages. I think in 10 years, this will really be happening. I think in 10 years, the first set of people will start going up who don't have to be billionaires to do so.
Yeah, so that's kind of the follow-up to this question, was how long and what are the chances of tourism getting cheaper for normal people to try it? And what would you consider normal for normal people? Like how cheap could it get?
Right. Well, the cost curve is hopefully and by intention going to do something very analogous to what happened with commercial aviation. So, we weren't alive then, but commercial aviation started after the Lindbergh Prize was offered for the first transatlantic flight. That essentially spurred the commercial aviation sector as so many people competed for that prize. And so in the 1930s, the beginning of commercial aviation happens. The mail is being carried that way. And yes, rich people are starting to travel in pressurized aircraft, not as high as they go now. The cost then was such that only rich people could do it. The commercial aviation was for the very wealthy until after the Second War. And then after the Second World War, and especially in the last 30 years, the prices come down dramatically as the safety has gone up. And so the space pioneers are hoping exactly the same thing happens. They say that something that initially could be quite risky and very expensive will gradually come down in price and stay safe, and then the market expands dramatically. And that virtuous cycle means you can offer it cheaper and cheaper. Virgin Galactic, who were charging $250,000 for their suborbital flight. A full orbital flight on that same spectrum would probably be $5 to $10 million. So this is current prices, and we just imagine that in 10 years, say, these prices possibly, if there are enough players competing, could come down by an order of magnitude. And at that point, it becomes $25,000 for a suborbital flight and maybe a few $100,000 for orbital flight in a decade. And that's still a lot of money. But there's actually people who easily spend $25,000 on a fancy cruise or a fancy holiday. So the suborbital flight is now in the realm of a fancy vacation on Earth. And then with another 10 years, maybe the Earth orbit option will come down to that price. And at that point, middle-class people can do it.
The next question is from Panda Tech. What do you think about how machine learning and artificial intelligence will influence astronomy research work or further space exploration in the long run?
So machine learning and AI methods are already heavily used in astronomy. Machine learning is now used in almost all sectors of astronomy. It's used in extragalactic astronomy and cosmology, my field. It's used to identify faint signals, at or just below the level of detection, whereas simple algorithms sometimes fail, but machine learning techniques can home in on really faint signals and difficult to detect things in any application. That's very successful. Machine learning is used to classify things. It's used to classify galaxies. It's used to classify light curves for exoplanets, and pretty much pick any field of astronomy. And machine learning is often used to assist the humans, the experts that try and dig signals out of data and noise. So machine learning is now very present in astronomy in almost every field. And that will only continue. I think in terms of space program, it's also heavily used. It's starting to be used in design work. It's being used in modeling of space environments, in hypothesizing what kind of habitats we might want when we live off Earth, and so on. So it's very widespread. The tools are coming into just a standard toolkit that any astronomer would use.
The next question is from Mark Laufenberg, who, whether he knows it or not, asked a great question right up your alley. I recently read that some quasars are no bigger than our solar system, but are more luminous than entire galaxies. However, the article didn't explain the source of the energy needed to produce this incredible luminosity from such a relatively small object. Can you fill me in?
That's right. So it is pretty extraordinary to have something that's, some factor bigger than the solar system, maybe 5-10 times bigger than the solar system, that packs the energy of an entire galaxy, or maybe 100 times a full galaxy's light. So the heart of this is a black hole, a supermassive black hole, hundreds of millions, and in this case, we're talking about billions of solar masses, ranging, I think, up to the most massive, which is about 20 billion solar masses. The black hole is black, as always, but it's surrounded by an accretion disk. And the accretion disk for such a massive black hole is an incredibly efficient gravitational engine. What do I mean by that? I mean that the environment around the black hole, so outside the event horizon, is a situation of such extreme energy production possibility, because you're essentially turning gravitational potential energy into radiant energy, that the efficiency of this process can be about 40%, by which I mean the conversion of mass into energy is 40%. Now remember, in a star like the sun, the fusion process is converting mass into energy with an efficiency of 0.7% in the proton-proton cycle. So you have an energy efficiency mechanism from black holes that's 40 or 50 times more efficient than stellar fusion. And then you have an incredibly massive object doing it. So that, sort of in a nutshell, is how you can get such incredible energy out of such a small volume.
ASMK, who's on with us live, says, I have heard that pictures of galaxies have to be classified manually. Is this because it is hard to write an algorithm for it, or because scientists are still working on developing it?
Actually, it's now no longer true that it has to be done manually. So certainly historically, galaxies were classified manually. So through the early days of extragalactic astronomy, from the discovery of galaxies, 1929, through the First War, and then after, in the age of photography, the surveys were not so deep or so large that you didn't have samples that weren't maybe hundreds or thousands of galaxies. And at that level, it is not too hard for a human to classify. But as we entered the era of CCDs and surveys like the Sloan Digital Sky Survey, the number of galaxies in the surveys went past millions to tens or hundreds of millions. And at that point, there's no hope of classifying them by hand. Meanwhile, alongside, we have citizen science projects like Galaxy Zoo, where amateurs have been shown to classify galaxies just as well as professional scientists. And so we have this little interesting activity where we show that we don't need professional astronomers to do this, that self-motivated and trained amateur scientists can do it just as well as professionals. But now this has all been swept away by machine learning. So AI and machine learning techniques applied to galaxy classification are extremely successful, and they can be scaled to tens or hundreds of millions of galaxies. And the papers doing this have started to appear in the last few years. So really, nobody's going to have to hand classify galaxies anymore. Of course, astronomers still go in and random spot check what the machine learning is doing to make sure it's not messing up. And those spot checks essentially show that it's doing a great job, and we don't need to get people doing it by hand anymore.
The next question is from one of our live participants who has an unpronounceable handle. So in 1911, I think, Rutherford threw alpha particles and suggested the nucleus model, or the solar system model of an atom instead of the plum pudding model. But aren't alpha particles nuclei? So how did he know what it is that he was throwing or shooting at these other sources?
Yeah, so this is a classic physics experiment, and one of the most famous physics experiments probably in history, the Rutherford experiments of the early part of the 20th century. Ernest Rutherford was a New Zealand-born physicist who worked most of his career at the University of Cambridge. And of course, the lab he worked in is now named after him, the Rutherford Lab, and it still does physics experiments. So this classic experiment, he was able to use radioactive decay to generate alpha particles. So that's just a decay product of standard radioactive decay, some types of radioactive decay. And the alpha particle is indeed a helium nucleus. It's 2 protons and 2 neutrons. So it's a tiny size of a nucleus, size of atomic nucleus particle. His experiment involved sending those alpha particles in a beam, so letting them only travel in one narrow cone going forward through a gold foil. So he got the thinnest possible gold foil he could get, and he shone the alpha particles through that foil. Now, to the eye, that foil was solid. It reflected light. If you pushed on it with your finger, it was not very strong, but it was a solid surface. But to the alpha particles, they just went straight through. So that was a very dramatic result of his experiment, that the alpha particles passed through the gold foil as if it weren't there at all. And from that, Rutherford inferred that normal matter, normal atoms, as in a gold matrix in a foil, consist mostly of empty space, and that most of the mass is concentrated in a tiny, dense atomic nucleus with the electrons orbiting or circulating outside it. So that was the influence, idea of his experiment. Another fact of his experiment was that some very small fraction of the alpha particles deflected by large angles or bounced back in the direction they came from. And he found that very surprising. And he used that to bolster the idea that there was a tiny nugget-like mass, the atomic nucleus in the gold atom, that had most of the mass. And when the alpha particle, another tiny dense nugget of mass, hit it, it just recoiled and came back out. So mostly empty space, but with a large fraction of the atomic mass in a tiny nucleus. Those are the implications of his beautiful and classic physics experiment.
The next question is from Z Astro, who's on with us live. And the first question, it's kind of 2 questions. One should be fairly easy, but is a white hole real? And what would happen if a white hole were to collide with a black hole?
So the question about the reality of white holes is we don't know. And they are very speculative objects in physics. I mean, you can have things in physics that are, wildly or mildly speculative. And I guess white holes are closer to the wildly than the mildly. For example, faster than light particles, tachyons. There are some variants of theories of physics that predict faster than light particles. So I'd say those are mildly speculative, but never been observed. White holes are more wildly speculative because we don't know of a mechanism by which a space-time, portal could exist from which energy could emerge. We know about black holes, which is the one-way trip where the radiation and the matter goes in and nothing comes out. But the reverse of that is very speculative, and I don't think there's any evidence to support it. So we don't think white holes exist at the moment. And then the second question of what would happen if a white hole and a black hole met is, of course, equally hypothetical and speculative, because if we don't know that white holes exist, then the odds of a white hole and a black hole colliding are very slim. And I don't even think mathematically we know what would happen. It's possible that the white hole and the black hole would just subsume each other into what really looks mostly like a black hole. That is a piece of space-time that's hidden from view.
The next question, and I believe this will be the last question for today because we are at the end of our time. Igerzoom asks, are there any theories that a singularity could reach some kind of critical rotation velocity, perhaps the speed of light, that could balance its immense gravity and allow other interesting things to happen? And I can do a follow-up when you finish that.
Sure. So singularities are the imputed density cusps at the center of black holes. And indeed, for a stationary black hole, you predict just a simple cusp, an infinite mass density at the center. In the theory of general relativity, the black hole's rotating. It is true that in the math, the singularity can possibly extend into a ring-type configuration. So you can finesse the idea. It may still have infinite mass density along its one dimension, which is a strange concept as well. So the singularity takes on a different nature in a rotating black hole. We have no experimental evidence for what that nature is, since we can't peer into black holes. So again, it's pure speculation in general relativity.
And sorry, so I guess one thing that I guess we could do a quick follow-up with is I'm sorry, hang on, I lost the question. So why do we look for or speculate about sort of hypothetical things like black holes? What's the use of that in scientific circles? I think it's a really interesting question to end on because there have been other sort of hypothetical situations that have turned out to be fruitful. So maybe you can talk about that and we can wrap up with that.
Okay, so the issue of what is hypothetical and speculative and what eventually is a fruitful line of discussion, that's an interesting one. And you have to look at the history of science, especially of physics, to judge this. Black holes are a really good example because black holes are indeed predicted as a consequence of general relativity, a successful theory of gravity. Very soon after Einstein formulated it, he didn't believe they were real. He thought they were mathematical artifacts. So even the architect of the theory did not trust his own theory in what it predicted, which was black holes. It took other theorists to work through the math of the black holes, and then it took astronomers decades later, in 1969, the first black hole was actually observed, Cygnus X1, to show that black holes exist in the universe. So it's an interesting example of something that even the architect of the theory didn't believe that is eventually shown to be real, and now we study them fairly routinely. So there are other examples like that, and I suppose that example alone would lead you to believe that you should be bold in your theorizing and your speculating, that if a theory predicts something, you should imagine that it might be real. The other classic example from physics is, of course, use of the quantum theory to predict the existence of antimatter. So when you solve the Schrödinger equation for a situation where you form particles and antiparticles out of energy, there are two solutions, and one is the standard particle solution, and the other appears to involve the square root of a negative number, which is an imaginary index, and that corresponds to antimatter. Now, nobody knew what antimatter was when the theory was proposed, and it was only 15 years later that Philip Anderson observed a positron in a physics experiment, and so we detected the first antiparticle. And again, at the time, Dirac, of course, trusted the quantum theory, but there were other quantum physicists who didn't think this other solution to the equation was real. They just thought it was a mathematical thing. So those two good examples show that we should probably be bold in our speculation based on physical theories that we have reason to believe describe the universe, because many of their implications that we can't yet test might end up being testable and true. Okay, it was a good question to ask. And on sort of a philosophy of science question, and good conversation and questions this week as always. We'll be back with you next week. Thanks for participating. Thanks to Matthew for facilitating, and Alexander for getting us rolling, and Vicky too in our live stream. Okay, goodbye.
Excellent. Thank you all for joining us. We have our next live stream will be on YouTube next Tuesday at 10 o'clock Mountain Standard Time. And we have then the week after that, we'll send out the announcements. Take care, everyone.